So to everyone who is on, I'd like to say good morning, good afternoon, or good evening, depending on exactly where you are. My name is Mike Hudak, and I am the principal investigator for the Applied Geodynamics Laboratory, more commonly known as AGL. And this is a webinar designed to introduce people to the AGL, who we are, what we do, and in particular, if you're a prospective member company, why it might be advantageous for you to join the consortium. So let me just start off by saying, well, what is the Applied Geodynamics Laboratory? Well, it's a consortium. It's funded by generally companies in the oil and gas industry, and it's run from the Bureau of Economic Geology at the University of Texas at Austin. So everybody who works here is one way or another an employee of the University of Texas at Austin or is affiliated with UT Austin. So the full-time people who work here, or mostly full-time, we have 9 professional scientists. We have specialties ranging from structural geology to sedimentology and stratigraphy and geotechnical engineering. And AGL was founded in 1989 by Martin Jackson and to study salt tectonics, which is certainly what we are best known for. And we've studied pretty much exclusively salt tectonics until about 5 years ago when we began to add shale tectonics to our research portfolio. So what you're going to be seeing today is some mixture of our research in both salt tectonics and shale tectonics. In 2022, we had 19 member companies. They're listed here. So you can see, get an idea of some of the people anyway that are involved. And since we started in 1989, that gives us, 33 years of history. Now, during those 33 years, we've had a role in quite a lot of conceptual development of salt tectonics. Some of the major concepts developed are presented on this slide. You can also see the last few down in the bottom right are some of the concepts in the world of shale tectonics that we have been involved in developing. And I'll be going into a little bit more detail about some of these as we go along. So we've had a long history. We've been quite prominent, I would say, in the development of modern salt tectonic theory and geometries and so forth. And we are increasing our roles in the world of shale tectonics. So all these ideas, all the things that we've come up with one way or another, where do we get the ideas for doing that kind of research? Well, it mostly comes from our member companies. And that's, in fact, one of the enticements that we hold out for joining AGL is the role that you can have in helping to define our future research directions and to an extent control what it is we work on. So sometimes that's as simple as just a topic that comes up in a visit to a company and we all say, that would be an interesting thing to work on. And there are other times when the interaction and collaboration is much more direct, where the companies involved provide us with data or let us come sit in their workspaces for a while. And we have a very strongly collaborative research program with an individual company. And some of those, the more intensive collaborations, are presented here. We have an ongoing collaboration with ExxonMobil and PGS in offshore Cyprus, another ongoing collaboration in Trinidad with Woodside and PGS, past collaborations in offshore Mexico with both CGG and Pemex, and the list goes on. All right, so that's a little bit about the background of AGL. Let me now talk about the purposes of this presentation. Why are we having a webinar? Good question. Well, the first one is to recruit companies to join AGL. With COVID happening, the oil industry was hit pretty hard during COVID, and because we're downstream of the oil industry, we got hit a bit too. So we are looking to rebuild and refocus our research program. And so we're looking for more companies to support us, to support our research and give us a stronger ability to research what you need. Now, to give an explanation of what we can do, I mean, why should any given company join AGL? Well, there are probably some companies out there in which we're not a good fit. There's nothing we can do that could really meet your needs. But some of the things that we can provide, which I hope will be resonate with some of you. First of all, guidelines for seismic interpretation around salt and mobile shale. We've had a lot of experience. We also have a pretty deep understanding of the physical modeling and the numerical modeling that can sometimes come in very handy when you're trying to decide what to do in an interpretation around a salt structure. So first one is guidelines for seismic interpretation. Along that, because we do have some emphasis in reservoir geometry and deposition, understanding trap and reservoir distribution around salt. Where are the viable places to go? Where is it likely to have a viable trap? Where is it less likely? We've also done a lot of work in the regional understanding of both salt and shale tectonics. So this is, by regional, I mean sort of basin scale or sub-basin scale. What's going on in an area with shortening, extension, compression? How are the structures linked with one another, and so forth? Trying to help people understand the regional setting of their particular problems. And with our emphases on numerical modeling and geomechanical modeling, we've developed a number of different models for stress and pore pressure around salt to give people explanations for what they are seeing and maybe some predictive capacity to try to understand a little bit about what you might be seeing in a given wellbore or going to see in a wellbore that's going to be drilled in the future. And finally, application to particular problems for your company. And this gets back into the collaborative nature of some of our research. We have done and continue to do projects on a variety of scales for individual companies dealing with their specific problems. And these can range all the way from a few days to weeks or months, depending on the scale of the problem and the financial setup of how we want to do that. So there's a variety of different things that AGL can provide. And our hope is that at least some items on that list may ring a bell for you. So that's the completion of the overview of AGL. Now I want to talk a little bit about what it is we do and who it is that does it. So our staff and research methods. And a real key to AGL is the fact that we approach salt tectonic and shale tectonic problems using a variety of different methods and tools. We sometimes call this our three-legged stool of geologic studies, physical modeling, and geomechanical modeling. And the way this works is that the geological studies, which are in real salt basins, give us an idea of what is there. What are the geometries we're looking at? What are the regional configurations we need to try to understand? So it kind of embeds us in the real world of salt tectonics and exactly what it is that we're trying to explain. Then we use the physical modeling once we have some idea of what the geometries are that we're concerned with and the boundary conditions that we're concerned with. We use the physical modeling to try and understand what is controlling what. In other words, the kinematics. How do these structures form? If we have an idea from the geological studies, we test those in the physical modeling. We also use the physical modeling to investigate the sensitivity to different boundary conditions. What happens if we double the shortening rate? What happens if we have a basin that is narrowing down dip, and so on and so forth? We ask a lot of what if questions in the physical modeling to try to gain a better picture for exactly how the setup of an individual basin may be controlling the types of structures we see. And then we go to geomechanical modeling, which really deals with the physics of the problems. What exactly are the stresses? What are the pore pressures? How does overpressure develop? How does the salt exert stresses on the surrounding rocks? How do the surrounding rocks exert stresses on the salt? And so really come to a fairly deep level physics understanding of what exactly is going on. And then all of that can feed back into our interpretation in the geologic studies. Now that we understand the kinematics and the mechanics, that can help guide the seismic interpretation in geologic studies and so forth. So it makes a loop. So let's talk about each one of these three technical disciplines that we have in order. We'll start with the geologic studies. In terms of personnel, this is the largest group in AGL. You can see the list of people who are involved in the geologic studies. And these geologic studies involve a number of different approaches to trying to understand the natural world, the salt basins that we're dealing with. Probably the most fundamental one is seismic interpretation. That's what we probably spend most of our time doing, is various levels of seismic interpretation. This is just one example showing a slice on the top, a slice with the pinch out of the Luan salt, which is the black stuff around the edge, the northeastern edge of the Gulf of Mexico salt basin. And you can see where the black goes to the white. That is a kind of a weird looking geometry. And down in the bottom, we have from Lake Powell in the United States, we have a picture of what drowned river valleys look like. And there is more than a passing resemblance between the pinch out of the Luan salt and the configuration of drowned river valleys. And so we've hypothesized that, at least in this part of the Gulf of Mexico, the Luan salt was deposited following some kind of rise in water level that drowned a series of river valleys, and that's the environment in which the salt was deposited. So seismic is probably our primary means of investigating real salt basins, although it's not the only one. What you can see here is one way we have of analyzing the geometries we see when we look at seismic data, which is structural restoration. We have several people who are quite expert in doing structural restorations, and we use this to try to figure out from the geometries that we're seeing in our geologic studies what likely evolutionary scenarios might look like. And this, of course, we're going to feed into our physical modeling program to try to investigate if what we think we find in the structural restorations are actually what we see when we try to model the stuff. So seismic data, structural restorations, and then finally field projects are all major components of what we do in our geologic studies. Field projects are outcrops, in short. And it's true that salt basins are in general not terribly well exposed at the Earth's surface because salt has the nasty habit of dissolving. But there are still a number of places where you can see structures involving salt. The Great Kavir in Iran is actually an area of actively depositing salt as we speak. So that provides fascinating insights and possible analogies to past depositional environments of salt. And then we do a lot with exposed salt provinces. For example, the Albanides in Greece and Albania. A fold and thrust belt detached on salt and involving diapirs is a very interesting place to do research, as is the High Atlas in Morocco. And the Albanides and the High Atlas are both, and the Great Kavir are also current areas of research with us. So these are some of our current field projects. There are many more past areas of research. So that gives a quick overview of our geologic studies group. We look at seismic data, we look at field examples, we do structural restorations, all trying to understand what the geometries of real-world salt structures are, and then something about how they formed. Now that understanding gets passed off to our physical modeling program, which is run by Tim Dooley. He's a structural geologist who specializes in doing physical modeling. And you get a couple pictures of Tim's lab. It's one of the more high-tech labs in existence in the world right now, and you'll see some of the sorts of things that Tim can do in his lab. So with this, we do a couple of different scales of investigation. One is regional analysis, where we take a salt basin and set up boundary conditions and try to see what's controlling what. So this is part one of a series of experiments that Tim has done, trying to simulate the Bay of Campeche, which is the southern Gulf of Mexico. Here's a model which has shortening going on because there's orogenic shortening in the Bay of Campeche. This model had, 41 pre-existing diapirs buried in the subsurface. And so we're looking here at the geometries that you get when you take a salt basin, in this case, a salt basin that narrows northwards, a salt basin with pre-existing diapirs, and you shorten it. And of course, what you find out is that the diapirs and the narrowing of the salt basin both have a pretty profound impact on the sorts of geometries that you get. And then we compare this with what we actually see in the basin, and we start to gain an understanding of what parts of the geometry are controlled by what. So we begin to understand a little bit more about what is controlling the final geometries that we see. Now, one of the things Tim is able to do in these modeling is slice them up at the end. And then with all these slices, you can effectively build a three-dimensional model of the structure, which you can look at with CAT scan software, with medical imaging software. And here's a model of a series of welded salt walls that extruded salt sheets at the top. You're looking at the three-dimensional geometry of the salt here. And you can see by looking at some of the feeders how there are these little patches and gaps in the salt walls. And those are the areas where the structure has welded. And so we begin to gain some understanding in this of the three-dimensional geometry of the welds. So this ability to do three-dimensional or build three-dimensional models of the salt is a very powerful tool because it also enables us to slice the models in various different directions. So this is more on the scale of individual structures as compared to the first models, which were showing regional analysis of salt tectonics. Another type of individual structure that we've started looking at in recent years are layered evaporite sequences, where you have what we show here is three different sections from a model where on the top you're looking at something that's pure salt. Salt is the gray translucent looking stuff. The middle one is a salt layer with one layered event, well, layering non-salt layer, which is this kind of red unit in it. And the bottom one is with two units within the layered evaporite sequence, two non-salt layers within the layered evaporite sequence. And you can see that the structural style of the extensional geometries are very strongly controlled by exactly how the salt is layered. So using experiments like this, we can begin to understand how the mechanical layering of the salt actually controls what's going on. At this point, actually at the start, I should have mentioned that this is all being recorded, so now you know. And also, if you want to ask any questions about this, you can type them in chat or in the Q&A, I guess. And or at the end, I believe there'll be a chance for you to raise your hand and we'll unmute you and you can ask questions directly. All right, so this is the physical modeling program that we have. So we've talked about the geologic studies, the physical modeling wing, and then the geomechanical modeling run by Maria Nicolanaco and Mari Heydari. They are both geotechnical engineers by background, although they have, at this point, they've been with us for many years. They've gained a quite considerable understanding of geology at this point. And so this is where we try to understand the physics of what's going on, of exactly what is happening in here to make the salt behave like it does. And we do several types of analysis in this. For example, this is a model of a mobile shale layer, which is the orange unit at the bottom. I'll play it. And this is right now just showing the sequence of events. So the mobile shale is the orange, the sediments deposited on top are the gray, and you can see a shale chord anticline forming at the left side of this model. Now, one of the nice things about doing anything with geomechanical modeling is that you don't just get the geometries, you can query it for all sorts of physics properties. So at the top left, you see the stress ratio. So exactly, where is the shear stress high? And red means that we're very high. So in no great surprise, we're seeing some very highly stressed stuff in the core of the fold. You can also keep track of fluid pressures. So here's where the overpressure ratio is, and consistent with what many people already believe about mobile shales, you can see that our overpressures are quite high in the core of the fold. So we use these physical modeling to investigate shale tectonic structures. Just in general around salt, there's quite a lot we can do measuring both overpressure and stress. So for example, here is an extensional salt structure, and we are looking at a comparison in the evolution of the same structure. In the top one, we allow fluid flow across the fault from one side to the other. And in the other one, we allow fluid flow only along the fault. And you can see how the overpressure distribution, which what the colors are strongly modified by this. So this is one of the nice things about geomechanical modeling is that you have almost infinite capacity to change one parameter at a time and see exactly what is controlling what in terms of the physics. We also have expanded this to doing three-dimensional work. This is from an area called Mad Dog Field. This has been in collaboration with BP. The sort of whitish, grayish blobs are salt. So you're looking at a big allochthonous salt sheet over the top. There is a dome here. There's actually underneath the sheet, there's another dome and so forth. And we are looking at the overpressure along a particular reservoir level and using this to try to understand how overpressure develops and how overpressure is distributed and what the controls are on how the overpressure is distributed. So it's not just two-dimensional models, but it gets to be fully 3D. All right, so that is an overview of the types of work we do. We do geologic studies, we do physical modeling, we do numerical modeling. And then we apply these three disciplines to a variety of different research projects. And at the broadest level, we have three of these projects. First is salt tectonics, which is certainly what we are best known for. The second one is shale tectonics. which again is the last 5 years. And then the third one, which you could call a subset of salt tectonics, except it's dealing with a whole different set of problems and at a very different scale, is the role of salt in the energy transition. So what is the energy transition? Well, it is the anticipated transition to a hydrogen-based economy rather than a hydrocarbon-based economy, and also deals with issues involving carbon capture and storage, or CCS. So what roles do salt tectonics have in that? Ollie Duffy has just published a paper 2 weeks ago, I think, on this. And we'll talk about some of the research that we're doing right now to support the energy transition or define the role that salt tectonics can have in this transition. So in each of these, what you're going to see is that our three areas of research, the geologic studies, the physical modeling, and the numerical modeling, they all apply to each one of these. So we're going to start with salt tectonics. So in terms of the geologic studies, we do geologic studies, well, really around the world, but wherever we get good data. And so we've got projects going in the Gulf of Mexico. We've got active work going in the North Sea, the Eastern Mediterranean. This is offshore Cyprus. And you can see, of course, that the geology looks radically different in all three of these areas. And this gets back to the fact that what goes on in your basin is a really fundamental control on how the salt structures evolve, because it's not like there's just one type of salt structures that you see everywhere you go. You actually get very different geometries depending what part of the world you're in. So we do a lot of geologic studies in basins around the world on salt tectonics. And then similarly, salt tectonics is one of the fundamental aspects of Tim Dooley's research in physical modeling. And this just provides a little bit of an overview on some of the stuff that Tim's been working on. The upper left, welded salt walls, where you take a salt wall, as in this black, one of these black things, and you squeeze them shut. And what does that look like? And sometimes they just squeeze shut simply, sometimes they're cut by overthrusts, and you can get all sorts of interesting geometries. The bottom shows mini basins sinking into a layered evaporite sequence. This has application particularly to offshore Brazil, and looking at the kind of welding or the deformation that you get underneath the mini basin when it tries to weld through this layered evaporite sequence. And you can see in this one, this has reached the stage of breaking up the layered evaporites into little pieces. And some things are trapped in a weld. Some places you end up actually being able to have the mini basin weld directly against the substrate. And again, with many things, you can do this three-dimensional imaging, which is what's shown on the right. This is a salt wall that grew in one of Tim's models. And somewhat contra the usual model of salt walls are just big, long, linear things where every cross-section looks the same as you cross the wall. We've actually been seeing quite a lot of variability in the way that salt walls develop through time and along strike. And this is based on some work that Tim and Oliver Duffy have been doing in the North Sea, for example. And there's a lot of North Sea salt structures which resemble this quite closely. And we're beginning to try to investigate, well, what is it that causes a salt structure to grow to look like this? All right, so we've talked about salt tectonics, the geologic studies. We've talked about physical modeling of salt tectonics, the geomechanical modeling of salt tectonics. Well, a wide range of things being done. This top one shows the stresses that occur associated with welding of a diapir, squeezing a diapir shut. And you can see that we start to develop some very high stresses next to the weld. And actually, interestingly, we start to develop very high stresses even before the welding is complete, which was a somewhat unanticipated result. We have looked at, in the bottom left, development of crustal faulting above salt structures. The salt structure is in black at the bottom of this section. And how exactly stretching of one of these structures, or even just rise of one of these structures, stresses the roof rocks over the top, develops normal faults, and so forth. And one of the more recent developments in what we're doing, shown in the lower right, is we have the ability to interactively generate new faults. One of the longstanding issues in geomechanical modeling is in many cases you have to predefine your faults. You have to decide before you start where the faults are going to form, because you need to condition the model to with the pre-existing faults in them. And there is now technology in the software we're using that enables you to grow new faults wherever a new fault would want to form spontaneously. And so we are doing modeling, investigating how faults form, where they form, what is it about the salt tectonics that makes the faults around salt structures form the way they do. All right, so that's salt tectonics, geomechanical modeling, physical modeling, and numerical modeling. Now let's talk about shale tectonics. Geologic studies in shale tectonics. Again, we are working in multiple basins on this. The Gulf of Mexico has some fascinating shale tectonics. Even though the basin is better known for salt tectonics, there is still quite a lot of shale tectonics going on mixed in with it. We've got a project going on in offshore Trinidad, shown here, where very interesting mud volcanoes, mostly now buried, although not all of them, formed in association with a very complicated network of thrust faults. And then a very interesting project in offshore Cyprus, again involving salt in the red, but the salt is sitting on top of a mobile shale. And you can see in the lower right of this image that the base of our salt is actually being deformed by shale diapirs. And so we are investigating the processes by which a mobile shale, in this case, mobile shale that is underneath salt, is interacting with the salt and is making all sorts of very interesting structures, and how this is all happening in a big passive margin. So we have an active program of geologic studies involved in trying to understand mobile shale behavior. Juan Soto is probably the premier researcher that we have. That's his main focus. But then we also have geomechanical modeling. And this diagram in the upper left, which is probably looking fairly incomprehensible to you and actually would take quite a bit of explaining, is a shorthand to saying that we have developed a mechanical model for mobile shales. And this, to us, was a pretty major research accomplishment, that we can actually understand why it is that some shales become mobile, some shales do not become mobile, and what are the geologic conditions that control whether a shale becomes mobile or not. And the short answer is that we believe that shales become mobile when they reach something called critical state, which is sort of a soil mechanics term equivalent to failure, the more familiar term of failure for most geologists. So mobile shales have to fail in order to become mobile. And having this kind of a mechanical model, a geomechanical model, allows us to do several things. For the first part, it enables us to be able to come up with some sort of material model to put into numerical models so that we can begin to simulate the behavior of mobile shales. And in this particular one, this is the model I showed you before, we're showing how close things are to critical state. And essentially what you need to know is that the red is at failure, is at critical state. And so you can see that the mobile shale layer, which is the layer that's mostly red, you can see how it forms. Also that there are little patches of things within the mobile shale that are not at failure. Only parts of the mobile shale are currently at failure and flowing as you build this structure. Now, having a mechanical model for mobile shales also enables us to simulate them in physical models, because you can pick an appropriate physical modeling material to simulate this kind of behavior. So I will play on the left. This is just a picture of how the model evolves, and our mobile shale analog is in here. And at the moment, it sort of looks like it's just deforming like salt deforms. You know, just looking at this, I don't know if this is a mobile shale model or a salt model, although this kind of big duplexy thing at the back looks very strange. I've not seen that in a salt model before. But because of the way Tim has set up his lab and some of the software that he uses, we are also able to look at this model and look at the strains going on inside this model. So here, purple is unstrained, and then the hotter colors represent higher levels of strain. And what you can see is that our mobile shale analog is not deforming uniformly. In fact, there are very discrete shear zones that are going through it, while other parts of it remain completely unstrained. So there's a little patch of unstrained material in here that is surrounding by some sort of anastomosing network of shear zones. So although the overall geometry is somewhat reminiscent of what we get in our salt modeling, actually what's happening inside is very, very, very different. And that is consistent with what we see in field outcrops of mobile shales as well. They do not uniformly flow. There are these anastomosing shear zones running around. So we're very excited about some of the advances that Tim is making in the physical modeling. So in summary, the shale modeling, we've got the geologic studies going on, we've got here the physical modeling, and in the numerical modeling, we are able to simulate the behavior of mobile shales because we think we have a fairly robust geomechanical model of exactly how mobile shales deform. And that brings us to our last topic, which is salt in the energy transition. Now, salt has a bunch of roles in the energy transition, only some of which we are looking at. Salt can influence certainly heat flow. So geothermal energy can be highly influenced by salt tectonics, and you can use salt structures to try to understand heat flow better and try to develop actually fields to collect the heat. It also helps control the distribution of the sands and other porous media around the salt. That comes into particular use when you're trying to do carbon capture. But the one we're focusing on at present is using salt as an area for storage of, well, whatever it is you're trying to store. So hydrogen, for one thing, if we're going to transition to a hydrogen economy, we need vast quantities of probably underground storage, and salt is right now the only tested means of doing that. Similarly, carbon dioxide can be stored, nuclear waste can be stored, all sorts of things can be stored in caverns dissolved out of the salt. Now, the one big problem with that is that people who make caverns for a living live in fear of what are sometimes called anomalous zones, or non-salt lithologies that are mixed in with the salt. And so we are trying to understand the distribution of these non-halite units inside the salt to, in the end, be able to predict their occurrence and provide guidance for where you should and shouldn't try to put caverns. We show here on the left, these are some of our geologic studies aimed at this. We've come up with some conceptual models for where intrasalt shear zones should and should not occur and what types of intrasalt shear zones they may be. And on the right, you're looking at an actual example of internal structures inside a salt diapir. This is from the Great Kavir in Iran again. The diapir outline is kind of the edge of this domiform feature. And you can see there's all sorts of layering inside the salt, which has complex deformation. And again, we're trying to predict, or in the long run, trying to predict where these sorts of impurities may be most concentrated and where it is away from these impurities that would be the prime locations to be putting a cavern. So those are some of the geologic studies. We're also doing the same thing with physical modeling. Here are some of Tim's models where we sank a series of mini basins. And the mini basins are these multicolored, sandy looking things that sank into a layered evaporite sequence, a sequence with a whole bunch of impure layers. And you can see that diapirs grew between the mini basins and that these layers within the evaporites end up getting very complexly folded into the diapirs. The depth slice on the left, shows the mini basins as the big circular features. And what you see inside the salt that is in between the mini basins are this series of very complex folds involving the impure layers. So again, trying to understand exactly where it is that you should be putting caverns and where you have a higher likelihood of running into some of these impurities, which can mess up with your cavern development and cause problems in cavern stability and so forth. So that's the physical modeling. And then there is geomechanical modeling, trying to understand exactly what it is that's going on inside the salt that can control, again, differences in salt rheology or where you put the weak layers. So the model on the left is showing if you have a fault offsetting the top of your salt. So the sediments are in gray, the salt is in the colors, and exactly how that fault propagates into the salt. Is there a shear zone in the salt that propagates in from any faults that are outside the salt? And if so, I mean, how does that depend on the formation of such a shear zone, depend on the extension rate? How does it depend on the presence of impure layers inside the salt? How does it depend on the viscosity of the salt? And so on and so forth. Again, one of the big advantages of geomechanical modeling is that you can almost infinitely vary your parameters and just ask the question, what if, all the time. On the right is another geomechanical model, this time showing several weak layers, sort of meant to represent something like a sylvite or a carnallite or something like that inside the salt. These are these thin layers in the overall blue, and just exactly how they get deformed and distributed in the rise of a diapir. So this was a model that started out with flat salt, then we made the diapir grow, and you see how some of these weak layers end up being distributed and how they accommodate differential strain. So there's quite a lot that can be done. We're really just starting to scratch the surface in our geomechanical modeling, trying to understand how anomalous zones develop inside salt. Okay, so this has provided an overview both of the types of work we do, the geologic studies, the physical modeling, the numerical modeling, and also the uses to which we put that expertise. We try to investigate salt tectonics, we try to investigate shale tectonics, and here the internal structures of salt domes for use in salt and the energy transition. So again, one of the primary purposes of this talk is to try to recruit people into AGL. So let me just talk to close out the talk for a few minutes about AGL membership, what it means, what you can get from it, and so forth. So what are the benefits of being an AGL member company? Well, first of all, as I mentioned, you get a chance to help direct our research. So we do our research based on what we perceive to be problems that our member companies are experiencing. And so if you are a member company, we'll be talking with you. And what we'll be trying to identify is good research projects that can help to solve some of the issues that you're dealing with. You also get to send as many people as you want to the AGL annual meeting, which is held in the fall. That is certainly convenient for companies in the United States. For overseas companies, it's a little less convenient. So we are now taking to rebroadcasting our annual meetings a month or two afterwards, usually in January. So we've got if you can't come to the meeting in person, we run these at, well, very early in the morning for us so that people, for example, in Asia and Europe can both attend. So you get to attend as much as you want at the annual meeting. We also put all of our annual meeting presentations, which are videoed, along with the PowerPoint presentations that were shown, on our website, which member companies can access. And we give 1 day of free in-house consulting each year. So you can have one of our scientists come to your company. You would pay travel costs, but you would not be charged any consulting fee. And we will come to your company upon request when we can set it up. So those are the broad scale benefits. What does it cost? It costs $55,000 a year. Which of course always sounds like a lot, but compare it to the cost of an employee and we're actually pretty cheap. Also, you have the option when you join of paying a $100,000 one-time payment, which gives you access to all of our previous work going back to 1989. This is actually the page where you choose on our website which year you want to look at. And if you click on one of these, you go to the list of PowerPoint presentations. You can download all of the PowerPoints. You can also play any of the videos and just watch the presentations given live. And all of this, going back to 1989, it cost $20 million for us to do all that, $27 million for us to do all this research. So you can buy $27 million of research for $100,000 one-time payment. We consider that a deal. We hope that you would consider that a deal as well. And so because we are currently trying to recruit member companies, this year what we're doing is we are visiting prospective member companies at our expense in 2023. That means you don't even pay travel costs. So if you're living in a part of the world where the University of Texas will allow me to travel or will allow us to travel, we'll come visit you. And in fact, I'm going to be spending 5 weeks in Europe, leaving about 3 weeks from now. And I still have some spots in my schedule. So if you are a European company, I I encourage you to contact me this week because I'll be making my plane reservations at the end of this week or early next week. But there's still time for you to get on to my schedule visiting Europe. But later in the year, I've got trips planned to USA and Mexico, to Central and South America, the Middle East, Africa, Asia, Australia, pretty much wherever a company is that wants to talk to me, I'll be traveling there. Most of these will take place in June and July, but if I can't fit everybody into June and July, we'll do it a little bit later in the year. So if you think you might be interested in AGL, or at least in seeing what we can do for you, I'd ask you to contact me and I'll come visit, which is the last slide. So if you're thinking about joining AGL or you'd at least like to schedule a visit, send me an email, and the email's listed here. And you can also just type in Mike Hudak, Salt Tectonics, and find me on the web pretty easily. So we encourage any companies that even are just thinking about it to give us a call, and we'd love to talk to you and come visit you and see if it would make sense for you to join the AGL consortium. So with that, that is the end of my presentation. And if we have any questions, I'll be glad to take them. So I believe Tim and Ollie are monitoring chat and Q&A. Or you can type in chat and Q&A, or you can just raise your hand, and I believe we have the capacity to unmute your microphone, so you can just talk.
Yeah, thank you, Mike. There's no questions in the Q&A just yet. Neither in the chat. We'll give people a few moments to, I guess, compile their thoughts. I'm just looking at if anyone's got their hand raised. Now is a good time. Give people a few moments. People, nothing so far. Maybe you've covered everything, Mike.
Well, that's fine. We'll give everybody another minute or so, or at least you can be copying down my email address.
Just checking on. Well, as far as I can see, there's nothing coming in just yet. So,
okay.
Unless anyone else can see something that's not showing up on my computer.
All right. Well, in that case,
yes, actually, there are two questions in the chat.
I can't see those. Sorry.
Oh, well, Thiago is asking if it's possible to share the list of companies that are current members, and another gentleman has a question about the shale diapir in Brazil.
Okay. So the answer to the first question, yes, it is perfectly possible to do that. Let's just go back. So first of all, that is on our website, in the public part of our website. So you can go to the AGL website and back, and look it up. But I can certainly go back to the slide. There it is. So you can stare at that list as much as you want. But this is publicly available. If you type in Applied Geodynamics Laboratory Salt Tectonics, you'll find our website on a search engine, and this list is contained on our website. So Nancy, could you read the other question about Brazil?
I can try. I have, let's see. This is, have you developed any research in shale diapir in Recôncavo Basin in Brazil?
The Recôncavo Basin.
Or in Foz do Amazonas Basin?
Yes. So I have seen the salt tectonics in both of those, but we do not currently have any research going there because we are limited by where we have data. So if data were made available to us in either of those basins, I think we would be more than happy to look at it and try to do some research. I mean, certainly, well, I'm most familiar with Foz do Amazonas. I mean, there's spectacular shale structures there. I'm less familiar with the Reconcavo Basin. But we certainly would be interested in doing that, but we have not had the opportunity yet because we don't have the data. Good questions, both of them.
Is there any more? So someone else may have to take the lead on identifying these because they're not showing up for me. So
well, if there
able to...
aren't any more,
No,
we have
no more questions.
Okay. Well, then again, I'd like to thank you all for your attendance. And we will, I think, eventually be putting this whole thing on YouTube so that you can show it to other people. But we appreciate your being here and your interest. And we look forward to speaking with you in the future. So I'll say goodbye at this point.